Welcome to the LemnaTec Academy. With this video, we start another mini-series of 3 videos. I will talk about machine learning with Lambda Experiment and Lambda Grid, using root analysis as an example. The first 2 are quite long, but there was no meaningful way to split them further. In this first video, I will explain how to create a machine learning model for semantic segmentation for roots in rhizotrons. I will show how to label the images and run a first training round. In the second video, I add 2 more training rounds, including updating the labels. At the end, we'll use this model in Lambda Grid. In the third video, I will explain shortly how to create a machine learning model directly in Lambda Grid and what advantages and disadvantages we have with this approach. But now get into Lambda Experiment first. In order to create a machine learning model, we first need to identify images for the training and test sets. These data should cover all kinds of image types you expect in the future for this analysis. But note, we work here with little data by comparison. The huge machine learning models like ChatGPT are trained using millions or billions of texts or images. Neither we nor you can afford these amounts of data. Therefore, we have to work with what we have and create machine learning models which are specific to a task. On the flip side, that means they will work only within certain boundary conditions, such as the same image recording device, the same type of sample holder, the same perspective, similar soil, similar plants. The more effort you spend on labeling and training, the wider the range of the machine learning model will be. Therefore, your set of training images shall cover the expected range of situations you want to analyze with this model, but not more. In other words, it must be representative. Now let's have a look on the images. We want to create a model for sunflower. If you develop your first model using these tools, I suggest you start with a more specific model like I'm doing here. Once you get more experienced, you may try models with a wider scope. I was able to create a model that covers all 5 species in this experiment. But note, the exposure, soil and other boundary conditions are kept identical. First, let's find an exposure setting. Here we already see a challenge with analyzing roots. The main root is almost plain white, while the side roots are still quite faint. Let's try a higher exposure. The side roots looks better now. So let's try an even higher exposure. The side roots are even better now, but the main root lost even more detail. So let's check a lower exposure. We have more detail in the main root and fainter side roots. So let's work with an exposure range from R80,000 to R130,000. We will use these multiple exposures to make the model more robust. You should keep these values in mind. Now we will check the different snapshots to decide which of them we will use as training images. I will restrict myself now to an exposure of R120,000. I use this R120,000 here because I think we as humans can judge images best at these exposures. So let's find a representative set of training images. Here the root is still very small. In this image, the root is a bit larger, so we have more data. Let's add it to the training images. The roots are now much more developed. This image is quite similar to the previous, but a little lighter and probably contains more data. So take this one. This image is quite similar to the previous one. In this image, the soil starts to dry out from the top and the shoot is more pronounced. So we had a little more information here. So add this image. This is the last one, so I like to keep this as a test image. Since we have only 7 images to work with here, I like to use only 3 of them as training images. So we keep in mind we will use the images from the 22nd of February, the 27th of February, and the 4th of March. And we are going to use the exposures between R80,000 and R130,000. Now we switch to the Explorer section. In this section, we have only one AI tool available as of the recording of this video, so we will use this. This page is just empty yet. In this page, we can create and list models for different applications. Each model consists of a couple of iterations. These iterations are called jobs here. Training a machine learning model is an iterative process. You start with some data, label it, train your model, and apply it to more data. Then you can check the result of this model on additional data. Update your labels, add more images, and start another training process. You repeat this until you are satisfied with the result. But note, there are some caveats. You should never add all images to your training set. The true evaluation of your model is on the data not used for training. As your training cycle progresses, you will indirectly optimize the model to the available test data. This means they lose their power to measure their accuracy to some extent. It would be good, if possible, to add more test images in every round. Now let's start with creating a machine learning model. In this screen, we can do 2 things. On the left, we can change hyperparameters of this model. We call these hyperparameters because during the training of the model, many parameters of the model are defined by the training process itself. To distinguish between the parameters set by the training process and the parameters set by you, we call the latter hyperparameters. For this model we use here, we have essentially one parameter, the training depth. This defines how long the training will take. 1 is the shortest and 12 is the longest. But note, the runtime kind of grows exponentially with this parameter. On the right side of the screen, you find a description of the AI tool, and you can add some quality verdict of this model. This, of course, requires that your model has been finished yet. So let's start with a training depth of 2, and let's enter a more meaningful name for our model. Now we have our first model in our list and can start preparing it for training. Now we are on a page similar to the recordings page. First, we need to select the experiment and the camera labels. Now let's start labeling our first image. Above each image, you see now a bar with 3 buttons and a checkbox. Let's start with the middle button. If I press this button, the label tool opens. I will use R120,000 here because in my opinion it is best for humans to differentiate the structures. Now we are on the label tool. If you are new to this tool, it will show you this tutorial. It will appear every time you start this tool unless you check this box here. On the left we see the image we want to label, and on the right a couple of controls. At the top you see some predefined label classes. You can use these or you can redefine them. In this case we will just use 3 of the predefined label classes. Roots, shoots for the green shoots above the soil surface, and background for everything else, including soil. Below you have the label tools you can use. In this video I will use only some of them. There's another video which will explain the label tool in more detail. Some of these tools have a parameter like line width. Also in this section you find 3 modes: add, remove and export. We'll come to them in a moment. The rest of the options here are not of importance in the scope of this video. At the bottom we have the display options. For now we use only the display labels checkbox. Let's start actually adding labels. I will demonstrate here quickly 4 ways of doing this. First, we use the draw tool and draw the outline of the root. By the way, I suggest that you always start with labeling objects, meaning root and shoot hair, and not the background. If you're on add mode, this will add pixels to the label image. The label image is displayed as an overlay over the original image. If you draw a label at the wrong position, like the root here, we need to correct it somehow. You can switch then to remove and correct it. If you use expert drawing mode, you can do this in one go. If you press the left mouse button while drawing, the pixels are added. If you press the right mouse button while drawing, the pixels are removed. These 3 modes are available for all tools except for pick label, where it makes no sense. If you draw a closed form, as we did here, we can fill it using bucket fill. If this form was not closed, then bucket fill will fail. The label tool allows only a certain number of pixels to be painted at once. If this number is exceeded, it assumes that there was an error by the user. The second option is using a wider pen with the draw tool. If you want to draw a root, this can be quite useful, but less so for other kind of objects. You can select a 1, 3, 5 or 7 pixel wide pen. Another tool which can be useful sometimes is AutoShade. It fills pixels which are similar in color to the pixel you have clicked using some metric. You can control the reach of this tool with the sensitivity parameter. High values mean that colors must be very similar, resulting in small areas. Small numbers allow for more difference in the color and fill larger areas. It is important that the labels are precise. False labels are more dangerous to the training process than missing labels. This algorithm we use here works well if you label an image only partially. In fact, I encourage to label only 10 to 20% of each image. The rest will then serve as an in-image test set. One more thing. The edge of roots never precisely coincides with the border of pixels. Therefore, some pixel will cover part root and part background, or any other pair of 2 label classes. Therefore, it is a good idea to keep a small gap between 2 classes, especially between background and the other classes. You can define this using the neighbor block width here. By default, it's 0 for all classes except for background, where it is 1. The fourth tool I like to mention is free shape. This is particularly useful for the background after you've labeled the other classes. I just draw the outline. This even don't need to be closed. And the exterior gets filled unless it's already labeled or blocked. You can select all these tools by shortcuts. The free shape tool, for instance, is S, and the root class is 3. There are more shortcuts available. Check them in the help page from the menu. The label tool has also an undo and redo function. The number of undo steps depend on the size of your computer's memory. As you see, I even cover sometimes gaps in the root and label them as roots. The algorithm will learn that these two parts of the root are connected and belong to the same root. I think we have covered enough of the roots now, but we also need to label background at places which are further away from the root. I will do this now. This is no root. Neither is this, nor this, nor this. I think that are enough labels to begin with in this image. Once you have finished labeling, press the Save Label image entry from the menu or use the shortcut. If you started the label tool from LemnaExperiment, all file names are already defined. Now you can close the app. Once you have closed the label tool, the bar above the image has changed. There's a fourth button here. I think now is a good time to explain them. By the checkbox, you request that the model will be applied on this image. This is always true for training and validation set images. All other images are added to the test set by this checkbox. Test set images are not used for training. The green button tells that the image is part of the training set. We can change this to validation set or test set. The validation set contains labeled images which are not included in the training itself, but will serve as an internal quality control. You will see what that means in a moment. With the disk button, you can load labeled images you created elsewhere. The link button on the right is something more special. Look, all the images in this snapshot have been created with the same camera settings except for the exposure. This means they all have the same perspective and the same content except for exposure. In other words, each pixel in them represents the same content in reality. So we need to label just one of them and use the same label image for all of them, or at least a selected subset of them. This makes the model more agnostic of the exposure and increases its overall robustness. So we will link the labels from R120,000 to R130,000, R100,000 and R80,000. and we will add R110,000 and R90,000 to the test set images. Now we need to label 2 more images. Now we have 3 labeled images. We use each of them for 4 different exposures of the same content. We can start the training process now. You find 2 buttons at the bottom right. One defines the execution locations. However, this menu has no effect at the moment. The training is executed always at the same machine as you run Lemna experiment. In future versions, it will be possible to run the training on a remote analysis PC. With the other button, we start the training. This switches back to the models screen. If we open the sublist of the model, we see the individual training jobs. Here we can monitor the progress of our training. Once we reach 5% progress, we can switch to the training progress screen by clicking this button. On this screen, we can monitor how the quality of our model is improved during the training. It shows 4 plots representing different aspects of the model quality and their progress. On the top, we have the current value of the so-called loss function. This is a function the algorithm actually minimizes during the training. In a way, this loss function guides the training. At the bottom, we may look at some other metrics of the quality of the current model. We have two options here. Accuracy. This approach is 100% if all pixels in the respective set are predicted correctly. And error. This is the amount of pixels not yet predicted correctly. I prefer this since it's minimized during training and I can watch the progress at later stages better. On the left, we have the values for the training set. And on the right, we have the values of the validation set. The validation set contains a certain percentage of the labeled pixels from the training images, plus all labeled pixels in the images marked as validation set images. These are not used in the training process, but they are evaluated every 1000 iterations. Generally speaking, the values in the training sets are lower than those from the validation set. This is normal. The value of the training set will go down almost forever. However, at some point, the model quality itself, in terms of the predictive power, is diminishing. This can be measured by the values of the validation set. If they are ever increased, this indicates that we start overfitting. In this case, we need to add more labels and use maybe a shorter training depth. I said the values of the validation set shall not increase. That's true, but it's also true that there's some randomness to them. This randomness is normal and unavoidable. Only if the overall trend goes up, you shall be alarmed. You can press the refresh button on the right to update these plots. In the center below the plots, you see the completion of the training. Once we are finished with the training, we can go back to the Models page using the Models button. We have executed our first round of machine learning training. The results look promising, but we have to improve the model. We will do this in the next video. See you there.